I apologize for going over. Just kind of going here, rolled here, but I think we're learning a lot. I hope you are anyway.
I know the two questions I'm going to miss on the exam.
Yeah, the parallel. Well, those are the ones to practice on your own.
I know.
Okay. All right, we're going to try to wrap this one up and then go on to power factor, which is a different topic. But I think the rest of these things are more or less repeats of what we've been doing so far. Okay.
Thanks a lot, though.
Okay, good to see you, John. Take care. Okay, so we got down to this stage here, and I hope everyone, if you use your calculator on this, do this arithmetic and take the square root here. What you should come up with, if you do the calculations correctly, is 0.00414. And we've got now the 37 degrees to deal with. Oh, Lord, that's a pain. That's again involves the tangent. Let's see here. We've got the tangent, and it's going to be 0.0025, and point opposite is the. So we got. Let's see if this is 0.0025 divided by 0.0033. Take the tangent of that. Let's see, our tangent of that rather. And 37 degrees. Okay, so that's correct. So if we go back to the conversion here of our trigonometry, if we have here XL, or this thing, of the inductor was, let's see here, or the admittance of the inductor was 0.0025, and the resistance, the admittance of the resistor was 0.0033. We've got the arc tangent of 0.0025 divided by 0.33. And what do you come up with?
It's got to be less than 45.
Got to be less than 45, but what is it? You might know what it is. Got a picture.
37.
37 degrees, roughly 37 degrees. All right, we got only one step left in this thing. One step left in this monster. We've got to go from admittance back to impedance. So let's write down what we had here for admittance, and then we'll do the last step, and then say goodbye to this problem. So let's see what the total admittance is now. Total admittance Y is equal to 0.00414 with an angle here, and it was 37 degrees. And now we need to convert that back to impedance. We want to now get impedance. And there's a rule, and once again, there's a rule for doing it this, and it's, all I can say is study it. The rule is you take the inverse of this. So what's the inverse of 00414?
241.
It's 241?
Yeah,
Okay.
1.545.
Okay, we'll say 240. And here's a rule that I just have to tell you. When you go from admittance to inductance, you flip the sign of the angle. So it's with an angle. Actually, hold on. This was actually
Minus.
This was minus here. Yeah. So we have with an angle of plus 37 degrees. So that's that. After all of that calculation, is the answer.
240,
You know, you're just going to have to practice these problems. These are hard. I mean,
Remember, it's either A or C.
yeah. Well, unfortunately,
Switch those around.
they push those around. You know, either memorize the answer of these or learn how to do them. Take your choice. But they're not easy. In the interest of time, we're going to move on to power factor because I want to at least cover that to some degree. So let's talk about what power factor is. This will be a much easier, more relaxing topic than parallel impedance. I guarantee you. It's kind of interesting too, actually. The good news is most of the problems are series, and using what we've learned here, you're going to be able to solve virtually all of the series problems in your mind without even using a calculator. And the chances are you won't get a parallel. And if you do get a parallel, sorry.
Take your best shot.
Take your best shot. Okay, I remember my struggle last time with drawing shifted sine waves. I took care of that problem. Beautiful, huh? We're talking, in order to study power factor, we got to talk about phase shift. Because phase shift is everything's related to phase shift in power factor. When we had I will have to draw one sine wave here. When we have just a signal, sine wave generator going through a resistor, the voltage and current are in phase. If you plot them, you got a sine wave here, and when the voltage goes up, the current goes up. When the voltage goes down, the current goes down. When the voltage hits a peak, the current hits a peak. It follows Ohm's law, equals IR. Very simple, in phase. When you replace the resistor with a capacitor, well, let's do inductor first. No, I've got a capacitor on top. Let's do the capacitor first, because I've got my first chart as a capacitor. And we look at the voltage across the capacitor, and we look at the current through the capacitor, and put them on an oscilloscope. It looks like this. What happens is the voltage here, time is advancing this direction. What we see is that the current hits its minimum here, but the voltage doesn't hit its minimum here until a later time. The voltage is lagging behind the current in a capacitor. See this? Where does it get to the minimum at time 3 here on current? Where does it get down to the minimum here on voltage? At time, looks like about 4.8 or something like that. So there's a shift here when we put a capacitor in. When we change this to an inductor, the opposite occurs. Now, we look at it where the red is voltage. The voltage hits its minimum here, but the current hits its minimum at a later time. So it's shifted the other way. So in this case, the current is lagging behind the voltage if we have an inductor. Now I'm going to try to explain why this happens, because this is not an obvious thing. An inductor is like a heavy mass. I'm going to convert this into something you can understand, physical objects instead of electrical things. Imagine an inductor being a heavy object, like a cart that has a pile of books on it, but it has wheels on the bottom. You can move it, but it's heavy. Voltage is like force. In fact, we call it voltage. Electromotive force is another term for voltage. So we're going to say, in this analogy that I'm going to come up with here, that voltage equals force and current, I, is equal to speed. The faster the thing is moving, like when we have stuff flowing through, we have electrons flowing through a resistor, the more electrons that flow through, the more current we have. So the motion, the faster they're going, is more current. So we've got that analogy here in your mind? Okay, here we've got this cart sitting here, heavy cart, lots of books piled up. We're standing here. Right now the cart is still. That means the current is 0. There's no motion. Speed is 0. I want to accelerate this thing, so I begin to push on it. So I apply a lot of force, and immediately the force, when I start pushing, if I look here, my force goes from 0, I'm just holding onto the handle, and all of a sudden I apply a lot of force. My force goes up like this. I begin pushing. The speed started out at 0, but the speed is going to take a longer time to go up. So the speed, it's not going to hit its maximum here. The speed is going to come up later on after I've been pushing a while. So which one was leading here? The force was leading. See, that's right. So the voltage was leading here. I was applying the voltage first, but the speed increased later on after I'd applied the voltage. So the speed or current was lagging behind the force. Does this kind of make an intuitive feeling about how forces and speeds would change if you're pushing something? The same thing would be true if I get this thing going, I want to slow it down. Now I apply negative force. So I suddenly put a negative force on it, but it's still got a positive speed. And I have to apply a negative force for a while to get that thing to stop and start going back the other way.
It's like braking a car.
Like braking a car, that's right. So my force, my negative force was applied first, but it took it a while for that speed to respond to the negative force. The speed occurred later. So the speed lagged the force. Does this kind of make an intuitive sense? Well, inductors are like masses. They don't have momentum. They store the energy by building a magnetic field. But in terms of the concept of a force, which is voltage, and the response of an inductor, it is the same. That is why the current lags. Now we'll try to talk about a capacitor. This is a capacitor is kind of like a spring. Let's see here. Here I've got a spring attached to the wall, and I'm standing over here pushing against the spring. I start pushing against that spring. This is a compression spring. When I start pushing against the spring, it's in its relaxed state. So the force applied is very low because the spring, the spring is out here. Moving it just a little bit doesn't require much force. The further I go, the harder it's going to get to compress this thing. The spring, got the idea? I start pressing against it. It starts moving. The speed starts moving immediately, but the force is still very low because the spring is not compressed. So which one leads here? The speed starts increasing immediately, but the force doesn't build up until I compress the spring down. You see what I'm saying here? Think about a spring. Which one? You start pushing it, but the force is very low at the beginning when it's uncompressed, and the force gradually gets higher as you compress the spring. But the speed immediately goes up as soon as I start pressing, because it's not resisting me. It just, as soon as I start moving, it starts moving. But its speed gradually slows down as I compress it. So the force, in this case, is leading the speed is leading the force because the speed starts up immediately, but the force comes up later. That is why a capacitor. I don't know if that helps you or not, but this kind of thing kind of helps me out to understand why one would lead the other conceptually. Now that we've got that under our belts, we need to talk about power factor. Let's go back and we take this down for a second and draw a circuit on the blackboard. We can retire Eli. Good old Eli, he's going to help you out so much. Let's have a real simple circuit that has only a resistor. And let's look at the formula. We may have a voltmeter here measuring the voltage across this resistor, and I'm going to put an ammeter here measuring the current through the resistor. I have some sort of power supply over here. The formula for power is equal to E times I, where E is the voltage drop across the resistor and I is the current flowing through the resistor. That's one of our basic formulas, kind of like Ohm's law. That's a basic one. In the case of a resistor, that is true in both DC and AC circuits. At any instant of time, if we freeze the signal and we see what at that instant of time, what A is and V is, or V are, we can figure out what that power is at that instant of time. Now the power in a DC circuit is always the same because the voltage and the current they don't change in a DC circuit. But in an AC circuit, if you look at it, the voltage is constantly changing. It's going up and then going down, up and down. So what that means is the power is constantly changing. At any instant here along this curve, and it changes with time, but if we want to know what the power is at this particular point right here, we take whatever the value of voltage is at that time and whatever the current is at that time, multiply them together, and that's the instantaneous power at this time. At this point right here, the power is 0. So the power increases, goes down to 0. Now going down here, what happens here on this negative part is the current is flowing the other way through the resistor. And first it's flowing one way through the resistor, and then as the voltage changes, the current flows back in the opposite direction of the resistor. But the resistor dissipates power regardless of which direction the current's going through. It'd be kind of cool if the resistor got hot. You put the power through this way, it got cold if you put it this way. It doesn't work that way. Doesn't matter. You can turn the resistor around, turn the power around, it still get hot. Either way it's going, they get hot. They dissipate energy. So when it's going one direction, it gets hot. When it goes the other direction, it gets hot. Only at these points right here when it crosses 0 is it not producing any power. And if we look over time, there's an average amount. Now I've got a chart here. I'll just kind of show you this. Let's see here. This plots out the instantaneous power going through a resistor. Don't get freaked out by this. This is not complicated. The red line is voltage. The green line is current. Remember, voltage and current are going to be related by Ohm's law, equals IR. So if we watch this, as the voltage is up here, positive, the current is flowing in some direction. The amount of current depends on the resistor. We come down here and we cross 0, where voltage is 0, and the current is also 0. There's nothing pushing electrons through the resistor. We come down here in the negative range, we have a negative voltage, the current's moving the opposite direction, but it's still moving through the resistor. Now here, up here, this dark blue line here, this is the power curve. Remember, power is equal to E times I. So what we did at any point, we simply multiplied, if we look at like this point right here, take this current, whatever value it has, multiply it by this voltage, and we can plot it up here as the power. So this blue curve is simply the product of whatever values on the red curve and whatever values on the green curve. Now here's something very important to look at. And that is, remember your algebra here. If you have a positive times a positive, you get a positive. If you have a positive times a negative, you get a negative. If you have a negative times a positive, you get a negative. But if you have a negative times a negative, you get a positive. Remember that? So look what happens here. When they cross 0, both of them become negative. A negative times a negative is a positive. So look what happens to the power curve. So it comes down here to 0, but when they both go negative, it starts going back up again. Because we have a negative times a negative for the power, so the power goes up again. So if this is 0, the power dissipated at any instant of time is either, it could potentially be 0 at these 2 points, but any other potential point in time, it's positive, it's greater than 0. And that makes sense because whether the current's going this way or this way, it's producing power, putting up power. So do you understand that this makes sense? With these two in phase, the power is always positive or potentially 0 just for an instant of time. Now, what if we change this to have a capacitor or inductor, either one, instead of a resistor? Something interesting happens. Here we have a curve of an inductor or a capacitor. It's a little more complicated, but you're going to be able to handle this. You all are not going to confuse you once you understand it, and you're going to think this is kind of cool. Okay, once again, the voltage is red, the current is green, but we have, it's either a conductor, well, let's see, actually, we have current, let's see, voltage hits a minimum there, current hits, so current is lagging, that's to be an inductor. So this would be an inductor, current is lagging. Now, we do the same calculation, P equals ET times I. Well, when they're both positive up here, we multiply this times this, we come up with this. When we finally get down to 0 here on the voltage, 0 times whatever current that is 0. The blue line is power. But look what happens when we get down to here. Now, we have a negative value of voltage and a positive value of current during this phase right here. Well, a negative times a positive is a negative. So the power becomes negative. Remember, power is never negative with a resistor. But in this thing, the power becomes negative and goes down for a period of time, and then it goes positive, then it goes negative. Now, what the heck is negative power? I mean, that's kind of a mind-blowing concept, negative power. Well, to demonstrate that, I have brought in a sophisticated piece of laboratory equipment. Here it is. This is a sophisticated piece of laboratory equipment to illustrate this point. If I apply a force to this, a certain amount of energy goes into it. It didn't dissipate it, it stored it by stretching the spring. As I release it, it gives back that energy. It returns it. See, a resistor would be more like, here we have a resistor on a surface, AC voltage, resistors going back and forth. Every time I do this, some heat's going out. You know, if I did this long enough and fast enough, presumably I could make a fire, right? But when I go this way, I give out heat. When I go this way, I give out heat. Doesn't matter whether I'm going this way or this way, it generates heat, both directions. That's like resistance. When you start talking about a capacitor, it stores energy this way, and then when I reverse it, it gives back the energy. It didn't dissipate it. Now, technically, if you really want to look at it, there might be a little bit of heat generated from the the friction inside here, but for the majority of it, yeah, the majority of it, like a spring, the spring stores it and then it gives it back, stores it and gives it back. So a capacitor is like this, or an inductor. It stores the energy and then gives it back. Well, when it's giving it back, that is the negative energy. That's when it's returning power to the circuit. That's when it's discharging. So this negative energy concept in here is nothing more than the capacitor discharging and returning its stored power to the circuit. So some part of the circuit, we put power into the capacitor or inductor. At part of the cycle, we get power out of the inductor. Now, I realize that from an exercise point of view, when I'm doing this, you would think I'm doing work. But from a physics point of view, I'm not, because I put a certain amount of energy into it, and a certain amount of energy came out of it. So even though in the gym, you may be doing work doing this, in a physics class, you're not doing work. You're simply storing it and then getting it back, storing it and getting it back. That's what happens in a capacitor inductor. They don't dissipate it, they store it. And if you look at this over one whole cycle, what you'll see is it has the same amount of positive energy that it has of negative energy. They balance out. So that's why over one cycle, the net energy consumed, if you will, by a capacitor inductor is zero, because it has some positive and some negative. They're equal. So over one cycle, it simply stores it, gives it back, doesn't dissipate any, so it doesn't use any energy. Resistor uses energy and dissipates it as heat. Capacitor inductors do not. They store it and return it. Does this make sense so far?
I was just going to say,
Yes.
in a lot of people's minds, they think of power production. Power can be consumed, it can also be produced. In this case, you're talking about power consumption.
That's right.
So
That's
when
correct.
you have, negative power, that means negative consumption, or actually the production of power.
That's correct. It's returning power that's stored back into the system is what it's doing. So that is why that is why a capacitor inductor don't dissipate, consume power. If we now get to power factor, now that you got these two concepts down, but once you got this down, power factor is Fairly simple. Let's go back to our simple circuit here. Start out with just a resistor and a power supply. And we'll make it an AC power supply. And once again, we're going to put an ammeter here. We're going to put a voltmeter here and measure these two things. And we turn on the circuit and we measure a certain current, a certain voltage, and we can discover P equals E times R, I. Just make the measurements, put them in the circuits, E times I. Now, that makes perfect sense, and you all have probably done this and thought about this. This formula right here, power is equal to E times I, where we simply measure the voltage and measure the current and multiply them together, that is called apparent power. Because that's what it appears to be. If we just take the simple readings. Now notice we didn't do anything here to measure phase difference between voltage and current. We just measured how much current, how much voltage there were, and multiplied them. That's called apparent power, which is equal to E times I without accounting for phase shift. Simply the product of them. In the case of a resistor, apparent power is equal to true power. What is true power? True power is the actual amount of energy dissipated by this item. If we measure this, if we have a voltage of 12 volts and a current of 2 amps, it's 12 times 2, 24 watts. 24 watts are dissipated by this resistor. We measure it, it appears to be 24 watts. We, actually examine how quickly this heats something up to measure the true power, discover sure enough 24 watts been given off. Apparent power equals true power. That is the case for a resistor. What if we make this more complicated and we put an inductor in here with a resistor? Now we've got a different situation. Actually, we'll use two different voltmeters to kind of explain this a little better here. We'll have a voltmeter across the resistor, call this VR, and we'll have another voltmeter, call this VL, across the inductor. And we're going to have to also measure the whole thing. We'll call this big thing, the whole thing is V across the whole thing. Okay, we measure current, we measure voltage, and we multiply out P times E times I. And what we discover, if we actually do a laboratory experiment, how much heat comes out of this thing, is that the true power being dissipated by this is less than the apparent power. It's appeared to be using maybe 100 watts. We multiply this out, but the actual amount of heat coming out was maybe only 80 watts. Well, why is it that if we measured the voltage in amps and the apparent power is 100, how in the world can only 80 come out of it? And the answer is that the inductor over here is not dissipating any, it's simply storing it and returning it. The resistor is. The resistor is putting out real power. The inductor is storing it and returning it. The same thing would be true if we put a capacitor in here. Put a capacitor in here, and just like the spring, okay, capacitor is in series with resistor. The capacitor is not dissipating it, it's storing it. So we have real power dissipated in the resistor, we have power being stored and returned to the circuit in the capacitor or the inductor. Now here's a really important concept, and you can get the answer to some questions by just remembering this. Power is only dissipated by resistors. If you've got this circuit that has resistors and capacitors and inductors and so forth and so on, and they say a certain amount of current's flowing through it, whatever current is flowing through the resistor is dissipated as real power. Current through resistors is real power. Current through capacitors and inductors does not dissipate any power at all. It's stored and returned, but not dissipated. So you only have to think about resistors in terms of what is dissipating power. If the true power is less than the apparent power, then that means the power factor is less than 1. Here's the formula for power factor. Power factor is equal to true power divided by apparent power. So we've got a circuit that has a resistor and a capacitor. We measure the current through the whole thing and the voltage through it. We compute the apparent power, but then we put this thing in some sort of chamber and let it heat up and see how much power is really being dissipated by that quickly. Heats it up and discover that the true power is less than the apparent power. Let's just imagine that we measure this as being 100 watts true power, but when we actually put it in a chamber and see how quickly it heats it up, we see only 80 watts is being actually dissipated by this thing. Well, what we have here is 80 divided by 100, or 0.80 power factor. The power factor is less than 1. It's 0.80, because only 80% of the apparent power is actually being dissipated by the circuit as true power. And all of that's being dissipated by the resistor. None of it's being dissipated by the capacitor over here. The power factor can range from 0 up to, could be as small as 0, could be as large as 1. It can never be larger than 1. It can never be less than 0. It's always between 0 and 1. In the case of just a resistor, the power factor is always 1. In the case of just an inductor or just a capacitor, the power factor is always 0 because they don't dissipate power. If you have a combination of a resistor and a capacitor, a resistor and inductor, then the resistor dissipates power, the capacitor and inductor does not, and we have a power factor somewhere between 0 and 1. So power factor, yeah, Joe, you have...
The other term you see, power factor 1, is sometimes called unity power factor.
Yeah, that'd be a good term for it. Unity power factor. Let's see here. What I want to do. Okay, now, let's talk about how we calculate power factor with phase shift and so forth. By the way, let me just as an aside here, let's talk about practical stuff. In your home, when you have machines, like an air conditioner compressor, a motor, those things always have power factors less than 1. The amount depends on how well they design the machine. A typical number might be 0.8, 0.75, somewhere in that ballpark. The only thing in your house that has a power factor of 1 are incandescent light bulbs. Compact fluorescent light bulbs, and so forth all have a power factor less than 1. Everything in your house has a power factor less than 1 except for, well, that's not true, an incandescent light bulb or like the heating element in your stove or your clothes dryer, something like that. A pure resistance incandescent bulb, a heating element would have a power factor of 1. Everything else has a power factor somewhat less than 1. If we look at apparent power, P-A-R-E-N-T power, which is volts, measure the volts, and multiply by the amps. And when you see the rating of a device, and they're giving you the apparent power of this device, the units are VA. Like if you go home and look at your computer power supply or something else, some other air conditioner, whatever, it may say something like 500 VA. It doesn't say 500 watts. It says 500 VA. Why does it say 500 VA rather than 500 watts? Because this is apparent power. In other words, if you multiply the voltage times the current going into the thing, it's 500. But there's a phase shift. So it's not dissipating 500 watts. The true power might be 400 watts dissipated. That is W. W is watts, that's true power. So when you see W or watts, that's always true power. When you see VA, that's always apparent power. So the true power is actually composed of two parts. We're almost near the end here. Stick with me another 10 minutes. We'll finish this thing up. True power is a combination of real power and reactive power. It's not, you can't just add, it's not simply the sum of those two, it's a little more complicated than that. But the real power, if you, the true power has two parts to it. Actually, hold on. I should say apparent power, excuse me, I got that wrong. Apparent power is a combination of real power, also called true power, and reactive power. And where is the true power being dissipated? What part of the circuit is dissipating true power? Resistors, only resistors. Where is the reactive power going? Capacitors and inductors. Capacitors and inductors, they store it and give it back. But they appear, they appear to be using current. So we got the apparent power is a combination of the real power, the reactive power. Here's some good news for you. I mentioned that virtually everything in your house has a power factor less than 1. In fact, almost everything in your house is an inductor, except for the resistances. Look at a motor, electric motor, what do you got? It looks a lot like an inductor, doesn't it? Like coils of wire. Everything in there, it pretty much is an inductor. So your house, if you looked at your house, measured it, you'd have a lot of resistance, but you'd also have a fair amount of inductance from the outside, from the power meter looking into your house. So the apparent power is greater than the true power for your house. Good news, folks. You know that power meter outside, there's dial spinning and so forth, it's kind of large as motor, it's like motor sign. That is measuring true power. It's not measuring apparent power. That's why it's more complicated than, somewhat more complicated than just a voltmeter and an ammeter, because it's actually measuring true power. The nice thing, the good old kind electric company is only charging you for true power. They're not charging you for apparent power. Only true power on your electric bill. Now for big commercial companies, there's reasons why they don't like power factors less than 1. I won't get into it here. You can talk to me after class if you want to, but the electric company doesn't like you to have a power factor less than 1. They realize you're going to, but they don't like it. And if you're a big industrial company, aluminum plant, something like that, and you have a power factor that's way off, they charge you for having the power factor off. They may charge apparent power rather than true. But for the home residential user, it's measured in true power. And you don't have to be concerned about that. I mean, you're doing some things which are not ideal from the power grid point of view, but don't be concerned about it. Okay, the last thing is the calculation, the formula for calculating the power factor from the phase shift. It's quite simple. The power factor is equal to cosine of the phase shift. Theta, where theta is the phase shift. So if you have, let's do it. Everybody got a calculator here. So remember what resistor, we have 0 phase shift. Remember that? Compute the cosine of 0.
1.
Okay, everybody got a 1? What's the power factor of resistor? 1. Try the cosine of 90 degrees. 0. What's the power factor of a capacitor and inductor? 0. And what's the phase shift of a capacitor and inductor? 90 degrees. Gee, it actually works. Obviously, if you have something in between, if it's a phase shift of 30 degrees, the cosine of whatever cosine of 30 degrees is what the power factor is. So that is the amount that the current and voltage are shifted. That is it. Do you feel prepared for this exam? Go for it. Okay. Well, think about it. Go over this stuff. Remember these little, when you get to these problems, you pause and think about them a little bit. Think about that 45 degrees. Is it greater than 45 degrees? Is it inductive or capacitive? Positive or negative angles. Go back and look at Eli the Iceman, figure out leading and lagging. And I think once you begin to get into this stuff and use these things, it's going to become pretty simple to you. Okay. Okay, good to see you. Okay, hope it helped.